In this particular unit, we're going to take a look at the idea of sets and also extend that into some probability things. So some of this is a repeat of what you may have had in prob and stat already, but some of this is new stuff, and I think sets are one of those things. So in mathematics, we define a set to be what's called a well-defined collection of objects. And these objects could be numbers, results, or just simply a list of items. So for example, the set of states that border Iowa, that's a list of states that all share a border with Iowa. Minnesota, Wisconsin, Illinois, Missouri, Nebraska, South Dakota. Those 6 states all border Iowa. And the braces that you see on either end, they are used to designate the beginning and ending of a set, and the members of a set are sometimes called the elements of a set. Okay, now really quickly here, what do we mean by well-defined? What we mean by well-defined is you can have a common agreement on classifying what is in the set. Okay, so for example, if you have a set that has all of the third basemen that play in the major leagues, and you want to get a set that has all of the good third basemen in the major leagues, well, what's a good third baseman? I mean, they're all pretty good at that point, but obviously some might be better than others. So just something to think about, that you have to have common agreement on classifying what is in a set. It's got to be generally accepted that these things are factual. Along with sets comes a whole language in and of itself, and a lot of this will manifest itself in true-false questions that you will see in different parts of our exercises. This first one, which looks like a letter E, it's a Greek letter epsilon is what it is, and the meaning is an element of. Okay, so for example, let's just say that we had this set A, and we use capital letters to denote an entire set. And let's say that the elements of A were the numbers 1, 2, 3, and 4. Well, we could say that 3 is indeed an element of A. And that is how you can use that in some sort of context here. Now, as we all know, anytime we've got a slash through a symbol in mathematics, and you probably remember this from geometry, anytime we have that slash that goes through a symbol, it negates what that symbol means. So in this case, the slash would mean is not an element. So we could say, for example, that 5 is not an element of set A. Something that we can consider very carefully here. Another way that we can describe a set, if a set has a rather large number of members, then maybe it's a little bit easier to describe what they have in common. So, for example, instead of listing out all of the states of the United States, what we might do is we might use what's called this set builder notation. And you read it, oops, let me not use the braces there. You read it as the set of all x, and then that vertical bar means such that x has a property. And again, this is where the well-defined comes in, helps us to kind of decide a common agreement on things. So in this case, we might say the set of all x such that x is a U.S. state. And then that would cover all 50 states in one fell swoop. Another example would be the set of all z, such that z is an even number. Well, as we all know, there's like a whole bunch of even numbers. Boy, I'm having trouble with those. And you know, that's a common complaint I get from students, is that those brackets or those braces are sometimes hard to write, and you are correct. They are difficult until you get the hang of it. Lucky for you, I'm not going to be doing any style points on those. Okay, so that's what the set builder notation is, and you'll run into that from time to time to describe larger sets. Now this next one here, down at the bottom, this is what we call the empty set. And this is a set that has no elements. Pardon me here, as I'm having some difficulty writing and that sort of thing. There we go. A set that has no elements. That's entirely possible that you could have a set that has nothing in it. So, for example, you might have, this would be a really good one. A set that has no elements would be 6th graders at Waukee High School. My guess is there aren't any 6th graders attending Waukee High School. That would probably be what we would consider an empty set. Or it might be what's in between Mr. Winter's ears. Sorry, I couldn't resist. Okay, a couple of more things that we need to know about sets before we go on to a couple of quick examples here. This would mean C is a subset of D. Okay, and that means that all of C's elements are also in D. Okay, so let's kind of consider the set C, which has the elements 4, 5, and 6 in it. And then let's think about the set D, which I'm going to define as the set of all x such that x is greater than or equal to 3. Almost said 4, I'm on 3. Well, 4, 5, and 6 are all greater than 3, so C is definitely a subset there. All right, now, sometimes it helps if you have a limited universal set. A good example of a universal set would be like a deck of playing cards that has a limited number of elements of 52. Or maybe you're just considering the numbers 1 through 10. It would be just the set of all elements for a given scenario, and that scenario may change from time to time. And it helps if you have a universal set to understand what a complement is. So what is a complement? That's what this means right here. This is a complement, and it comes in 2 different varieties. You could either see this with a little prime mark next to your set name or a superscript C to indicate complement. And this is the elements that are in your universal set that are not in your named set. Okay, so let's kind of take a quick little example here. Let's say that our universal set has the numbers 1, 2, 3, all the way up to 10. Okay, and let's further say that we have set G, which is 1, 2, 5, 8, and 10. Okay, so what does that mean for the complement? Well, that means that the complement of set G, that's all the numbers that are in U that aren't in letter G already. So 3 and 4 and 6 and 7 and 9, those are the numbers that are in our universal set, but they are not in set G. We can just kind of skip past a little bit of this. You could probably write out the elements very easily. By the way, when we say natural numbers, we mean counting numbers. So this would be 1, 2, 3, and 4. And the days of the week that we have school, I don't know, I guess that depends on what's going on in the world at that point in time. So maybe it's all of them. But typically we know Monday all the way through Friday, those are days that we do have school during the course of a week. And is the empty set a subset of any set? The answer to that is a resounding yes. The empty set is a subset of any set. Okay, now let's talk a little bit more about subsets as we wrap up this video here. Think about the set 1 and 2, and that's our A set, and then 3, 4, and 5. Okay, so if I'm thinking about finding all the sets that are subsets of A, well, if it includes just 1, or just 2, or it's the empty set, and believe it or not, A can be a subset of itself, you have 4 subsets here. Okay? And what I want you to do is hit the pause button on the video here for just a moment, and I want you to see if you can come up with the sets that are all subsets of B, 3, 4, and 5. So hit the pause button and give it a shot. And as you come up with those subsets, you see that 3 by itself, 4 by itself, 5 by itself, 3 and 4, 4 and 5, 3 and 5, also the empty set, also 3, 4, 5. They're all subsets, and that's a total of 8 of them. So how many subsets are there if you have k elements? Well, the answer is 2 to the power of k. So if you have a set that has 5 elements in it, then that means it's going to have 2 to the 5th, or 32 distinct subsets. Kind of an interesting little thing that happens there. And it's easy to come up with because for every element, either it's in or it's out, and those are your choices to make the subset. Okay, well, I hope you've enjoyed this little introduction into the various notation and vocabulary behind sets.